start by thanking the organizers for inviting me here and giving me the opportunity to speak. I should especially thank them for letting me speak about something which has pretty much nothing to do with the main topics of the conference. So there's not going to be any graphs or matroids in this talk at all. But what I will talk about is something called Bootstrap percolation in a random subhypergraph. And this is based on joint work with Rob Morris and Natasha Morrison. Okay, sorry, I'm just catching my breath. Yeah, so before I get into the main focus of the talk, I thought I would just spend a bit of time to address what I mean by the words bootstrap percolation in a fairly general context. So bootstrap percolation refers to a family of processes for modeling propagation phenomena on a discrete set of sites. And so what I mean by propagation phenomenon is basically you should think of anything that spreads. So you could think of the way a rumor spreads in a social network, or a disease spreading through a population. And these processes usually have kind of three main properties in common. So the first is that at every stage of the process, each site is assigned to one of two states. So in this talk, I'll say that each site is either healthy or infected. You can obviously use other terminology, right? Some people say active or inactive or whatever you want. So the second thing has to do with the way in which the process evolves. So the way it typically works is that if you have a healthy site, then it becomes infected if you've got a lot of infected sites nearby. Okay, and I put the word nearby into quotes here because I'm not talking about necessarily a geometric. I don't mean it in necessarily a geometric sense. They're not like Euclidean distance or something like that. So nearby could mean like at a bounded distance in a graph, or for example, contained in the same hyperedge of a hypergraph, or something, any kind of local condition. The third kind of property is that infected sites remain infected forever. So once you become infected, you never recover. Okay, so I've already mentioned that these processes can model things like spreading rumors or spreading disease, but they've also been used to model things like information processing in neural networks and dynamics of ferromagnetism, among other things. If you were listening very closely to Sergey's talk yesterday, he mentioned some connection between bootstrap percolation and what their work on Hadwiger's conjecture. That's practically the closest I can connect my talk to any other talk in this conference. But okay, so this is bootstrap percolation in general. So I want to talk about a specific process, which I'm going to call the hypergraph bootstrap percolation. So just to make sure everyone's on the same page, I'll just quickly define what I mean by a hypergraph. So a hypergraph H is a pair V of H, E of H, where V of H is just a set of vertices. In this talk, it'll always be a finite set. And E of H is a collection of subsets of V of H, which we call hyperedges. Okay. And so obviously, if all the hyperedges have size 2, then the hypergraph is really nothing more than a graph. But this of course, generalizes graphs. Okay, so as a quick example, you could take this set of circles as being your vertices. And a hypergraph could look like this, where each of these kind of blob things, which encloses a set of vertices, and those sets of vertices we think of as hyperedges. Okay, so now let me tell you what I mean by hypergraph bootstrap percolation. So the process goes like this. So given a hypergraph H, in the H bootstrap process, you start with a set of infected vertices. The other vertices are healthy. And then the infection spreads in the following way. So a healthy vertex becomes infected if there exists a hyperedge in which it is the unique healthy vertex. Okay, so so another way to say it, how I've got it written on the slide, is that a healthy vertex becomes infected if it completes an infected hyperedge. It's the last healthy vertex. And a useful definition is to say that the initial infection, or the set of initially infected vertices, percolates if every vertex is eventually infected. Okay, so basically if the infection spreads everywhere, we say it percolates. Okay, just a quick example. So in this hypergraph now I've colored some of the vertices white and some of the vertices black. Let's say that the white vertices are healthy, the black vertices are infected. And so we can see how this will evolve. Okay, so here we see that we have this hyperedge of size 2 here, right? It has a unique healthy vertex. So the other vertex will become, this is the unique healthy vertex, sorry. So it'll become infected. This hyperedge of size 3 also has a unique healthy vertex. Let me just highlight them in pink. So after one step of the process, these guys will be infected. And now we see, after infecting those vertices, we see that this top hyperedge has a unique healthy vertex. Let me highlight it. So then that guy becomes infected. And now the process terminates because there are no more hyperedges with a unique healthy vertex. Okay. So in this case, the initial infection did not percolate because it's not the case that every vertex became infected. Okay, so yes, let me try to describe our main result. And it gets a bit technical. I'll try to, it's kind of going to be a kind of rough statement of the result. I'll try to fill in the gaps wherever they are. So, okay, so here's the setup. So H is going to be an R-uniform hypergraph, meaning that every hyperedge has size R. We assume that it's roughly D regular, meaning that every vertex is contained in approximately D hyperedges. Okay, so and then we assume that and D is going to be large, and we assume that the hypergraph is sufficiently well behaved, which that's something I'm kind of sweeping under the rug here. I can roughly say that this basically, kind of the most important thing here is that the codegrees are not too large, meaning, yes?
What is D large relative to?
It's just going to be, it'll kind of come later. There's going to be an epsilon later, and it's going to be large with respect to epsilon. Yeah. Right, so so well-behaved is something to do with the codegrees. You don't want, so if you take a small set of vertices, like 2 vertices, 3 vertices, something like that, you don't want them to be contained in too many hyperedges. That's, actually this idea of codegrees came up in Michelle's talk yesterday. Right, okay, so we have a hypergraph, and now we're going to take a random subhypergraph. I'll call it HQ for Q between 0 and 1. And the way we do this is just by taking the hypergraph H and then including each hyperedge with probability Q independently of all the others. So just flip a coin for every hyperedge, keep it with probability Q, throw it away with probability 1 minus Q. Okay, and yeah, this is sort of like, kind of, if you think of GMP, right, this is kind of like that, except that the underlying hypergraph is not necessarily a complete hypergraph. So we have a hypergraph, we took a random subhypergraph, now we take a random set of vertices. That's going to be our infection. So AP is a random subset of the vertex set of density P, meaning, of course, you flip a coin for every vertex with probability P, you infect it. With probability 1 minus P, it's healthy. Now, I can almost tell you, so we're trying to work out whether this is going to percolate or not. And I need some kind of conditions on Q in order for this to work. And okay, let me just say, like, I'm not really using this in maybe a standard way. So, so with these kind of less than symbols, you should think of as, there's some kind of polylogarithmic term factor missing here. So, so Q is like maybe some polylogarithmic thing in D divided by D, and I should point out that actually we haven't completely worked out the full range of Q that we can do this for. So, so there's another reason for kind of hiding it here. Okay. Okay, finally I can give you the conclusion. So the conclusion is that if this product, P to the R minus 2 times Q times D, is at least R minus 2 to the, I should point out one thing. So in this theorem, R is at least 3. So, so this hypergraph is not a graph, so we don't have any problem with 0 to the power of 0 here. So yeah, so if this product is at least this constant, depending only on r plus epsilon, then this random set of vertices percolates with probability tending to 1 as d tends to infinity. And kind of conversely, if this product is less than this same constant minus, again, an arbitrarily small epsilon, then the probability of percolation tends to 0. Or, in other words, it does not percolate with probability tending to 1. Okay, so there's a few things I want to highlight in this result. So one thing is that this gives what we call a sharp threshold, in the sense that, really this value here, this constant, we can say that if the kind of density, either the density of the hypergraph or the infection is big enough with respect to this kind of threshold, like it's slightly bigger or slightly smaller, that kind of tells us whether the percolation happens with high probability or low probability. And the other thing is that this result, of course, it applies to a wide range of hypergraphs. I mean, in order to believe me on that, you kind of have to trust that this well-behaved condition is rather mild, but yeah, but it is. It's not too bad. Okay, so this is the result. Let me just spend a few minutes telling you about how we prove it. Yeah, so I mean, naturally, okay, we have a random hypergraph, we have a random infection, we want to say if it percolates, right? I mean, you would think that you should, well, just do exactly what I said. You should take the random hypergraph, you should take the random infection, and somehow analyze how it spreads. But it actually turns out it can be useful to do things in a somewhat almost backwards order. So actually, rather than revealing the random hypergraph at the beginning, it actually makes sense to reveal it only slowly. So let me kind of explain how that works. So yeah, so we pretend we don't actually know the random hypergraph. We just have the entire hypergraph H. And we have the random infection AP. And now let's make a definition. So say that a hyperedge is open if it contains a unique healthy vertex. Okay? So you've got the hypergraph, you have the random infection. You can, of course, define the set of open hyperedges. You can pick them out, you can put them in a bag, okay? And pick one out at random. Okay, so pick an open hyperedge at random, and now, once we've picked it, we check whether it's in the random hypergraph or not, okay? If it's in the random hypergraph, then this vertex here should become infected. The unique healthy vertex should be infected because, I mean, that's the rule of the process. So if it's in the random hypergraph, then we infect its unique healthy vertex, and then we throw the hyperedge away. And if not, we just simply throw the hyperedge away, okay, without changing the infection. Okay, and then you can keep repeating this, right? Now you have a different set of open hyperedges, because in fact you may in fact have a different infection, or at least you have in this case you've thrown one away, so you have a smaller set of open hyperedges. You keep repeating this, and it's not hard to see that actually the infection at the end of the process will be the same as if you just ran the normal Bootstrap process. Okay, so then everything comes down to really tracking the number of these open hyperedges as the process evolves. What I mean by tracking is basically you want to show that the number of open hyperedges stays concentrated around a certain kind of trajectory throughout the process. So basically, yeah, in a probabilistic sense, it's concentrated. So one kind of usual approach for showing that a sequence of random variables stays concentrated around some trajectory is to use martingale concentration inequalities, something like a Zumma's inequality or Freeman's inequality, things like that. And so to do that, what you want to do is say, okay, you want to say what is the expected change in this random variable, and what's the maximum possible change, right? Even if it's unlikely, you need to sort of have some idea of the maximum possible change. In this case, though, it turns out that to express the one-step change in this random variable, it actually depends on a bunch of other random variables. I mean, if you think about it, it's not terribly hard to see. And the thing is, we need that these other random variables are concentrated if we want to get any kind of useful bounds on the number of open hyperedges. Okay. And then if you want to control these random variables, then you need to control other random variables, and this kind of goes on and on. Okay. But the nice thing is that at some point you end up with a kind of a closed system of random variables, in the sense that the one-step change in each random variable in the system depends on other random variables in the system. Okay, so you can express these changes in terms of other random variables in the system. And then what you want to do is basically apply some kind of martingale concentration inequality to all of these things at the same time. So actually you get like, all we wanted to do is show that the number of open hyperedges was concentrated, but we actually, in order to do that, need to show that a whole big family of random variables stay concentrated. And then in particular, the one that we care about is concentrated. And this general approach that I'm describing is something which is known as the differential equations method, which has been, well, it's a very powerful method which has been used to do things like analyzing the triangle free process, which gives the best known upper bounds on the Ramsey number R3K. So that's work due to Bowman and Kivash and Fitz-Ponteveros, Griffiths and Morris. And it has a lot of other applications recently. And yeah, so let me just, really just quickly connect this to some other work. So our result generalizes, in a fairly big way, it generalizes theorem of Crandy, Pellet, and Sudakov. And also applies some results for a variant of the so-called graph bootstrap process studied by Balog, Balabosh, and Morris, Angel and Kolesnik, and others. Okay, so that's all I have to say. Thank you for your attention.
All right, are there questions? Jeff?
Yeah.
Your result tells you what happens if everyone gets infected.
Yeah.
I'm so pretty worried if there's a big epidemic, right?
Right.
Can you say anything about that more generally?
Yeah, so actually it's kind of interesting. Like, so in this, so what turns out to happen in this kind of model, in this problem in particular, is that when the infection doesn't percolate, it usually stops fairly early. That's the kind of thing. So if the density of the infection gets over a certain kind of threshold, then it just goes out of control. So really, actually we proved that if this kind of density of the infection is small, then actually it's going to stop when the number of infected vertices is definitely sublinear, right? It's going to be quite small, and otherwise it infects everything, yeah.
Any other questions?